Welcome back. All right, so let's do the other example I have set up here, but for the second law of thermodynamics. We have liquid water at negative 10 degrees Celsius and positive 10 degrees Celsius. What will happen? Well, you can probably guess in one situation the water will freeze, in the other situation it will not. But we are going to go to a lot of effort to figure that out. That's okay. Now, to demonstrate what's going to happen, we are going to need to find the entropy change of the universe, which means we need the entropy change of the system and the entropy change of the surroundings. Now, I gave you the entropy change for freezing and the enthalpy change for freezing. Okay? So when water freezes, it loses 22.1 joules per Kelvin of entropy. And when water freezes, it also loses 6 kilojoules of heat. All right, so those are our two factoids. Now, the entropy change of the system is rather straightforward. It's just the entropy change of freezing. Delta S of the system is delta S of freezing, negative 22.1 joules per Kelvin. Boom, we're good to go. What about delta S of the surroundings? Well, the great thing about this is that we're talking about just, I didn't say anything special, so this is just, a constant pressure sort of situation. Delta H is equal to Q, and delta S of the surroundings is just Q divided by the temperature change of the surroundings. So now we have both of our entropy changes. We're going to need to calculate the entropy change of the surroundings, but that's easy enough. Delta S of the surroundings is just 6,000 joules positive. Okay, remember, the heat lost by the system is the heat gained by the surroundings, so it's positive 6,000 joules. And all I did was I changed from kilojoules to joules so that we would end up with the same units at the end. If you look at delta S of freezing up top, you'll see that it's reported in joules per Kelvin. I left temperature rather than actually putting in the temperature because we have two different temperatures, positive 10 degrees Celsius and negative 10 degrees Celsius. It's not a huge problem, just 6,000 joules divided by, you have to switch it over to Kelvin. Okay, remember this. Okay, pay attention to your units. That's very important. Okay, entropy is reported in joules per Kelvin. So 6,000 joules divided by 283.15 Kelvin. Remember, absolute zero is negative 273.15 degrees Celsius. So 0 degrees Celsius is 273.15 Kelvin. Or positive 10 degrees Celsius is 283.15 Kelvin. Okay. So 6,000 joules divided by 283.15 Kelvin gives us 21.2 joules per Kelvin for the entropy change of the surroundings at positive 10 degrees Celsius. And at negative 10 degrees Celsius, it's 6,000 joules divided by 263.15 Kelvin is 22.8 joules per Kelvin. Okay. Not a huge difference, but it makes a huge difference when we actually calculate the entropy change of the universe. So let's go ahead and do that. I clear off some room over at the right, and I remind you that delta S of the universe is delta S of the system plus delta S of the surroundings, and we have those numbers now. Okay, delta S of the system is just the delta S of freezing right up here up top, and delta S of the surroundings is what we just calculated. Okay, those two numbers over on the right, okay, because we have two different temperatures we're considering. So the delta S of the universe is negative 22.1 joules per Kelvin, that's the system, plus our two different temperatures, okay, at positive 10 degrees Celsius, it's 21.2 joules per Kelvin, and at negative 10 degrees Celsius, it's 22.8 joules per Kelvin, and that gives us the delta S of the universe is negative 0.9 joules per Kelvin at positive 10 degrees Celsius. And at negative 10 degrees Celsius, the entropy change of the universe is positive 0.7 joules per Kelvin. Meaning that water will not freeze at positive 10 degrees Celsius, and water will freeze at negative 10 degrees Celsius. Okay, that's a blindingly obvious result. but it is a very, very nice thing when you can go through this sort of stuff step by step and come up with the right answer. It always sucks when you do the work and come up with the wrong answer. Coming up with the right answer is a good thing. So the result we get out of this is that very often, actually all the time, the spontaneity of an event or a process is determined by the interplay of entropy, enthalpy, and temperature. Okay, that's what I really want you to get out of this, because that's what we're going to be moving on to, is looking at entropy, enthalpy, and temperature. SHT. Now, the third law of thermodynamics. Okay, remember Boltzmann's equation, S equals K log of W. And if W equals 1, then S equals K log of 1, or K times 0, and entropy is 0. Okay? And this is the interesting thing about the third law, is that a perfect, pure, crystalline solid without any movement will have 0 entropy. So as temperature decreases, the entropy of a substance decreases to 0. And this gives us an absolute 0. This is where absolute 0 comes from. Okay, that's the 0 point. Okay, you cannot get below that 0 temperature because you cannot have a negative entropy for a substance. And that's where the Kelvin scale comes from. It also means that we can measure the absolute value of entropy for any substance. I mean, you have to put in a little bit of effort, but you can do it. It's not something you can do for, say, enthalpy. You can't measure the absolute value of enthalpy or the internal energy of any system, but you can measure the entropy because you're measuring, with respect to the 0 point, okay, the 0 entropy at 0 Kelvin. So that's kind of neat. If you look in your textbook, you'll find a table with some entropy values in it, and that actually is the absolute entropy of those substances at room temperature, 298 Kelvin. So that is what entropy is actually reported in, is usually the absolute entropy of the substance at 298 Kelvin in joules per Kelvin. All right. Now, like I said, because of the second and third laws, we can measure the absolute entropy of any substance at any temperature. And people have been doing that for a while now. And that means that you can just look things up in a table and find the entropy change for pretty much any process. And it looks an awful lot like Hess's law. Okay? The change in entropy for a reaction is the products minus the reactants, multiplied by the coefficients from the balanced chemical reaction. Okay. So let's go ahead and walk through an example. Okay, hopefully you remember Hess's law. If you don't, look it up, practice, study. So our example is going to be the combustion of ethylene, marsh gas. Okay, this is, the will-o'-the-wisp. Okay. Ethylene, C2H4, is a gas, plus 3 oxygen is a gas, goes to form 2 carbon dioxide, gas, and 2 water, gas. Okay. Now, rule of thumb, is this going to increase or decrease in entropy? Well, you have 4 gas molecules on the left, 4 gas molecules on the right, and it looks like no change in entropy. Okay, that's our rule of thumb. Okay, let's work the numbers. Okay. Now, in your textbook, in chapter 16 there is a there's a table with a bunch of entropy values on them. Okay? And this is where I got those numbers from, straight out of your textbook. Okay? But be careful if you do this sort of problem. Find the correct entropy value, because the entropy value will change depending on if you're looking at a solid or liquid or a gas. So the entropy for ethylene is 219.5 joules per Kelvin mole. For oxygen, it's 205.3 joules per Kelvin mole. For carbon dioxide, 213.8 joules per Kelvin mole. And for water, it is 188.71 joules per Kelvin mole. Now notice a big difference with Hess's law, okay, with enthalpy. The entropy of a pure element is no longer 0. All right. The enthalpy, the delta H for a pure element, the delta H of formation, is 0. But for entropy, it's not 0. Okay, everything has a non-zero entropy at non-zero temperatures. All right. So delta S of the reaction is products minus reactants is equal to 2 times 213.8, that's carbon dioxide, plus 2 times 188.71, that's water, minus 1 times 219.5, that's the ethylene, or ethene, plus 3 times 205.3, that's our oxygen, giving us a delta S of reaction for this particular reaction of negative 30.38 joules per Kelvin. All right, that is not 0. Our rule of thumb is just a rule of thumb. Okay, moles of gas versus moles of gas. I mean, if you look, this 30.38, that's pretty small compared to the entropy of each individual gas. When you look at the total entropy at the start versus the total entropy at the finish, the change it's pretty small. But it's not 0. Okay? That rule of thumb, it's just a rule of thumb. It's a guideline. It's not going to get you the perfect answer. If you have the numbers available, the numbers are the only thing that are going to give you the exact answer. The last knuckle on your thumb, it's about an inch. But if you want to measure a distance accurately, you're going to need to actually get a ruler out. And this also works for other kinds of reactions, other kinds of processes. Okay? For example, the condensation of water. So condensation means you're going from a gas to a liquid. So gaseous water to liquid water. You look up the entropy for gaseous and liquid water on that table. That's 188.7 joules per Kelvin versus 69.91 joules per Kelvin. Delta S of the reaction is products minus reactants, is 69.91 minus 188.71. Gives you a delta S of a reaction of negative 118.8 joules per Kelvin. This absolutely matches what we would expect. Going from a gas to a liquid, you would expect a big decrease in entropy. Okay. So, so long as you can, put down the process in this form, beginning, going to end, you can do the delta S of reaction for that process. Easy peasy. And our next topic is going to be a big one, so I'm going to go ahead and leave that for the next lecture when we'll introduce Gibbs free energy.